All right, so hi everybody. In this video, we're going to revisit exactly the same problem as the one we studied in the previous video, Perturbation Methods H01, which is an introduction to multiple timescales. And the reason why I decided to revisit exactly the same problem is that I think also, although I tried to do it quite neat in the first version, I think it's also very important to see how people would probably tackle and solve this problem in real life, I want to say, so in what you would see in the scientific literature. And you will see that this is substantially different, and this is why I believe it's important to revisit the problem here. And so what you would typically see in a problem like this is first that you want to seek a solution of the problem which is expressed as a function of two time scale. So instead of having x of tau, you would just change it and write x of tau and t. Sometimes either using semicolon epsilon to indicate that we are looking for an asymptotic solution when epsilon is a small number. All right, I think that's a first problem here because you use the same symbol here, which might not be too much of a problem because now you have two arguments to this function instead of just one. But as people usually don't write the arguments, which is also something I'm used to do, it might be sometimes a little bit hard to understand exactly what's done. And then, as I introduced in the previous video too, if we introduce the two time scales, which is the fast time scale tau, which is the time scale that we keep, it's the basic time scale, and the slow time scale t, capital T, which is chosen here as epsilon times tau. I justified in the previous video why we use epsilon times tau and not any other power of epsilon. This is also something that is not necessarily always justified. But the thing is that if you try and if it works, well, this is exactly what you want it to do. That's the principle of a what is so-called a distinguished limit. And so what you would just write here is that you have a partial derivative with respect to tau plus epsilon times the partial derivative with respect to t. Okay, so this means that if you want to rewrite the original equation, you'll end up with, let me just write probably the second derivative, which is anyway something that anybody would probably do. Second derivative with tau to epsilon cross derivative and epsilon square second derivative with the slow time scale. So the original problem becomes second derivative with respect to x plus 2 epsilon cross derivative plus 2 epsilon times the first derivative. So that's a derivative with respect to tau plus x. And this is equal to order epsilon. All right, so that's basically the same equation as the one we met in the previous video. The only difference is that I kept the same symbol x instead of introducing y. All right, so then from here we can say that x, same as what we did before, is takes the form of a regular ansatz. We push this into the governing equation, and then what we see is that at leading order, the governing equation is second derivative with respect to tau of x 0 plus x 0 is equal to 0. And we have the two initial conditions. First derivative with respect to tau of x 0 at time tau 0. Oops, I think you see that's the trap in which we can fall. This is initial time, and this is equal to 0. All right, and sometimes what you would see in the literature is that you don't necessarily see this, and some people might write something that looks like that. The value of the function and its first derivative at tau is equal to 0. And that becomes slightly problematic, right? Because we know, of course, that x0 is a function of 2 arguments, but when this is not explicitly stated, it might become a little bit of a problem. All right, but let's keep going. If we want to solve this, then we can write x is a times cos. I think this is what we wrote. Sine and so forth. All right, that's an option, but what you would also regularly see in the literature, and this is what I wanted to introduce in this video mostly, is that you could, instead of using sine and cosine, you could use just exponentials, and that's sometimes helpful. Not so much in this problem where, in fact, the equation is just a linear equation, but when you have polynomial expressions of x, then the second option might be interesting. And so instead of writing sine and cosine, I would just write a times the exponential of I tau. All right, and just to make sure that x0 is something that is real, I will add the complex conjugate. And this is how this is typically written, plus cc to indicate we add a complex conjugate. All right, so it means nothing but a of t exponential I tau plus complex conjugate of a exponential of minus I tau. Okay, then we can compute the first derivative because we'll need it in the right-hand side. The first derivative with respect to tau of x0 is a. I will, as usual, I will drop the argument for a. We need to differentiate exponential I tau, so we have I exponential of I tau, and plus complex conjugate becomes, in fact, minus complex conjugate, because this is a multiplied by I exponential I tau minus I conjugate a exponential minus I tau. All right, or if you want, this is plus complex conjugate of the first term. All right, the thing to keep in mind is that you want this to be real at the end of the day. All right, so this is minus the first derivative of that complex conjugate, or plus the complex conjugate of the first term. And that's again not necessarily true, necessarily clear, because you might find different things in the literature. So we'll need the cross derivative over here to build the right-hand side. All right. So let me just differentiate once more with respect to capital T. No big problem here. And so the right-hand side, it's going to become. And that's what we did in the previous video. We push this on the right-hand side. All right, so the right-hand side is minus twice multiplied by the sum of the two derivatives. Of course, epsilon drops because this is what we have on the right-hand side at the following order. All right, I'm taking a few shortcuts over here, but my plan is to go right away to the secular terms. So we have minus twice I, a plus first derivative of a, multiplied by exponential I tau, plus complex conjugates of the first term. And so we have an equation here that will just provide, probably we could also have a look at the initial conditions, or let's first solve this equation. We'll look at the governing equations then after. We have, we want to cancel this term because we identified, because of the exponential I tau, which is composed of sine and cosines, we identified that this needs to vanish. All right, and this means that a plus a first derivative is equal to 0. And from the complex conjugate, of course, you obtain something that you're not so much interested in, because this is nothing but the complex conjugates, and that provides the same information. And so we have just a complex equation here for a, because a might be a complex number. So we can solve this for the real and the imaginary part, all right? But this is quite easy, of course, because the solution of that equation is that a is a certain initial value a0 multiplied by the exponential of minus capital T. Okay, that's the general solution. And of course, a0 might be complex. Might be complex in this approach. So let's just have a look at the initial conditions to determine the value of this complex number. It is good that we have two initial conditions, one on the position, one on the velocity, and these two conditions will give access to the real and the imaginary part, or the norm and the phase of that complex number. All right, so if we use the initial conditions, they would give, I will just copy them here. If you want to remember exactly where they come from, you should go back to the previous video. Initial conditions. And what we got yesterday in the previous video is that x1, when the time t, tau, and capital T are both equal to 0, this quantity is equal to 0. Sorry, we're not looking at those boundary conditions. The initial conditions were just copied over there above. I'm sorry for that. So let me just copy them here. And the first derivative with respect to tau of x0 should be equal to 0. All right, so the first one, we'll just say that in the expression for x0, which is here, all right, we need to replace capital T and tau, both of them by 0. All right, so what we have is when the time capital T is 0, so this is a0 here, multiplied by the exponential of 0, that's 1, plus the complex conjugate, that is equal to 1. And the second equation here, first derivative with respect to tau, that's an expression we have over there, plus the complex conjugate of this, or minus the conjugate, minus the derivative of that term. So what we have here is a0, exponential 0, so that's 1, minus I multiplied by a0 conjugate. All right, and you see that this is in fact plus the complex conjugate of what's in front, just to make sure the final result is something that is real. All right, but in fact this just tells us that a0 minus a0 transposed is equal to 0. All right, so that's what this equation tells us. All right, so if you combine them two, you find that a0 is equal to 1/2. And of course, this is the same for the complex conjugates. All right, and so it just means that the amplitude, possibly complex amplitude, is equal to 1/2, and it decreases exponentially. And so if you substitute this back into the expression for x, which is a function of tau and t, you obtain 1/2 exponential of minus t exponential I tau plus a complex conjugate of this expression, which is then plus 1/2 exponential minus t exponential minus I tau. And if we just factor out this quantity, you see that what remains is in fact nothing but the cosine of tau, right? Because this is, if you want, this is cos plus I sine, and this is cos minus I sine. And so the sum of these two is twice the cosine divided by 2. So what remains is the exponential of minus t multiplied by the cosine of tau. All right, and so that's exactly the same solution as the one we got yesterday. It's just derived in a slightly different manner. It's probably easier to deal with this approach as soon as we have on the right-hand side, as soon as we have things that are a little bit more elaborated, and as soon as we have powers of x0 on the right-hand side, it's going to be easier to compute a power of exponential I tau rather than cos to the third, all right? And so as soon as you'll deal with a Duffing equation or van der Pol equation, which are examples of nonlinear equations where there might be polynomial expressions or polynomial transformation of the unknown quantity, you'll see that this complex number notation is something that is quite standard. All right, so I hope this was clear. It was a short video just to show you a few tips and tricks on how to tackle multiple timescales solutions of differential equations.